Hey, welcome to Unit 4, Lesson 7b. Today we're going to continue reviewing exponential functions. I want to go over a couple things that seem to stump a few of you guys in recent homework problems. So in our first example, I want to help you understand the parts of an exponential function. So the expression 5 times 2 to the power of t gives the number of leaves in a plant as a function of the number of weeks since it was planted. And then our first question is, what does each part of this equation represent? And we know this is an exponential function, so we're going to be using our equation y equals a times b to the x, which you guys should be very familiar with by now. In the case of this problem, we know that the number 5 is the initial value, right? That's our a value. And in this case, we're talking about the number of leaves. So 5 is the initial amount of leaves on the plant. And the next number in the equation is 2, which is our b value, and we know this stands for the growth factor. And since this number is greater than 1, we know this is going to be an exponential growth problem. All right, and we know for our b value, it's equal to 1 plus the rate of change, right? For an exponential growth problem, in this case, that's going to be 1 plus 1 equals 2. So we know that it is doubling every week. And last we have our exponent, which is t, and we know that t stands for time, but very important to remember in this case, time is in number of weeks specifically. So what happens if we change one of the parts of these word problems? So in this example, we're talking about the plant in my house that has 12 leaves, but grows at the same rate as the first plant. So how does that change the equation? So let's break it down. In the first equation for the first plant, we had f of t, which equaled 5, which is 5 leaves, times 2 to the power of t. And we know that number 5 stood for the initial amount of leaves. And in this problem, the plant is starting off with 12 leaves rather than 5. So we are going to adjust this equation to reflect that. So we're going to change our a value to 12 here. But that growth rate remains the same. It remains at 2 raised to the power of t. All right, so all we changed was the a value here. And I want to give you guys an example. So we're going to plug in t equals 2 to both of these equations to show you guys sort of how that initial amount changes our outcome. And we plug in an amount of time. So in the first example, if we have f of 2 equals 5 times 2 to the power of 2, and solving that, we get 5 times 2 times 2, which equals 20. And for the second equation, for the second plant, f of 2 equals 12 times 2 raised to the power of 2, and that comes out to 12 times 2 times 2, which equals 48. And that number is a little bit higher than 20, so that shows us that that plant with more leaves will actually grow much faster, right? Because it's starting with a higher initial amount. Now we're going to change another part of the equation, and in this example we have a plant that also has 12 leaves, but this one is sick and loses 1/4 of its leaves every week. So what does this equation look like? Well, we know we're still working with our y equals a times b to the x equation, and we know a is our initial amount, and we're still starting off with 12 leaves in this case. So our a value is still 12, and our b value, which is our growth rate. So in our other example, our growth rate was 2, right? So the number of leaves was doubling every week. And in this example, it's losing 1/4 of its leaves every week. So if it's losing leaves rather than growing them, we know that the growth rate is going to change in this problem. And another way of saying it loses 1/4 of its leaves is to say that 3/4 of the leaves remain every week, and we want to write it in this form. We want to use 3/4 as our growth factor because we're basically taking into account the amount of leaves that stay every week. And when we plug in a value for x, we'll get the number of leaves that remain on the plant at the end of that week. And I want to point out, because our growth factor is less than 1, this is an exponential decay problem. Now I want to talk about adjusting the growth rate for different units of time. So in the last example, we were talking about leaves growing at a weekly rate. And now I want to know how many leaves my plant grows every single day. So how can we adjust the equation so it represents daily growth instead of weekly growth? So we know our equation for weekly growth, right? It's that f of t equals 12 times 2 to the power of t. And then if we want to find daily growth, we'll use that same equation. We'll take f of t equals 12 times 2. And this time it'll be to the power of t divided by 7, right? That takes into account the fact that there are 7 days in a week. So if I'm gonna rewrite this, I'm writing f of d equals 12 times 2 to the power of 1 over 7, right? And that 1 represents the fact that we want to know how many leaves grow in one day, and that's all raised to the power of d. Now I'm gonna plug that into my calculator, and I get 1.104, and I'm gonna write that as our final equation. And notice that our growth rate is still less than 2 because the plant grows less in one day than it does in 1 week.